In this chapter, we're going to talk about finding roots of equations. So we're going to go through several methods, looking at bracketing methods, including the bisection method, false position method, and we'll look at some open methods, including fixed point iteration and the Newton-Raphson method. And this video is just going to cover up to the end of the bisection method. So first we can talk a little bit about an introduction and kind of motivation for why we want to find roots of equations. So many engineering and design problems involve finding roots or zeros of equations. So essentially what this problem boils down to is that if we have a function in some interval a to b, we want to find the value of x in that interval that would make the function f of x equal to 0. So we have this function and we want to find the values of x that make it 0, and these values of x are called the roots of the equation. So we can consider a function, g, let's say, defined on the set of real numbers, that's equal to ax squared plus bx plus c, where a, b, and c are real numbers. We know that there are two analytical roots for this function given by the quadratic formula. So we can solve for the values of x that make this equation equal to 0 directly using this formula. And in this case, there are three options based on the value under the square root. So if this b squared minus 4ac is greater than 0, then we get two real roots. If it's equal to 0, then we get two equal real roots. So in the first case, we get two distinct real roots. And then in the third case, if b squared minus 4ac is less than 0, we get two complex conjugate roots. And for our work here, we're only interested in real roots. So in that case, when we are able to use the quadratic formula or in some other way rearrange the equation to find when x equals 0 directly, we can say that that is an analytical approach, but there are many functions whose roots cannot be found analytically. So for example, if we have a function e to the power negative x minus x, you can't just rearrange that for x to find when x equals 0 directly. And similarly with polynomial functions, higher order polynomials or other polynomial functions that we can't just rearrange or use the quadratic formula for or other formulas, we can't find an analytical solution to find the roots of these equations. So in these cases, we have to use numerical methods to determine the roots of equations like this. So one example in an engineering application is the Ramberg-Osgood equation, which describes the nonlinear relationship between stress and strain in a material near their yield point. So, for example, it says strain is this epsilon is equal to the stress, which is sigma, divided by the Young's modulus E plus K times sigma over E to the power n, where K and N are constants depending on the different material. So if we want to find the value of sigma that corresponds to a particular value of strain, for example, 5%, then essentially what we want to do is solve the equation sigma over E plus K times sigma over E to the power n minus 0.05 is equal to 0. And we can't just rearrange this and solve for sigma directly. We've got sigma here, and then we've got this sigma to the power n here. So we can't just easily rearrange this and find sigma analytically. Another example is using the Stefan-Boltzmann law that describes heat loss for a sphere. So if we want to find the temperature on the surface, this Ts, we have Ts here and then Ts to the fourth here. So we can't just find an analytical solution for the temperature. Another example is, if you recall the parachutist example from chapter 1, we were able to come up with a differential equation that describes the velocity over time. Now, if we wanted to find the drag coefficient c to produce a particular velocity, this would be like a design problem. So we want, if our drag coefficient was our design variable that we wanted to determine to be able to produce a desired velocity, then essentially what we have is this function of c given by gm over c times 1 minus e to the power minus c over mt minus our desired velocity v. So again, we've got c here as well as up in the exponent here, so we can't just easily find an analytical solution for this. So essentially, when we're finding roots of equations, the problem that we want to solve is given some function f of x, we want to determine the values of x such that f of x is equal to 0. So there are lots of ways that we can do this, and one of the simplest approaches is just a graphical method. So we plot the function on the domain of interest and visually inspect where the graph crosses the x-axis. So for example, we have this function f on our interval from -1 to 1, and we can see where it crosses the x-axis at these. So we can find these 3 roots graphically. So we've got a root somewhere around minus 0.55, and then another one around minus 0.2, and one at positive 0.65 or so. And whether these estimates have acceptable accuracy depends on the requirements of the problem. And we can zoom in using software to get better estimates if desired. So here we can get a bit more resolution on this estimate of this root. So graphical methods are generally not very accurate, but they are very useful. So it's always a good idea to plot the function before using any method. So regardless of whatever method you're going to use to come up with your final estimate, it's a good idea to plot the function in advance. So this is useful to tell us the number of roots in the region of interest. So in that previous example, we could see that there were 3 roots in our region of interest. This would also tell you if there are no roots in the region you're interested in. And it can determine the approximate location of the root, so give a good initial guess for your method, and can show us the shape and behavior of the function. So for example, we've got examples of a few different functions here and kind of what different types of behavior we can see when we plot the function over an interval. So in general, if the function values at either end of the interval, so f of a and f of b, so assuming our intervals here go from a to b, the value of the function at a is f of a, and the value of the function at b is f of b. So if f of a and f of b have the same sign, then either there will be no roots, like this first one here, or there will be an even number of roots like this one here. So we see that the sign, both f of a and f of b are positive, and there are 2 roots in that interval. If the function value at either end of the interval have opposite signs, so like this one and this one, then there will be an odd number of roots. So you can see here f of a is negative and f of b is positive, and there's 1 root in between, or in this case 3 roots in between, or there could be 5 or 7, etc. There are some exceptions to this, for example in the case of multiple roots. So in this case where the function is tangential to the x-axis, so here the f of a and f of b have opposite signs, but there are only 2 distinct roots in the interval. The other exception would be in discontinuous functions. So here f of a and f of b have opposite signs, but there are only 2 roots in the interval, and that's because the function is discontinuous. But in our course, we're only going to be concerned with continuous functions. So the alternative to graphical methods is using a root finding algorithm. So the 2 main types are bracketing methods and open methods. And there are essentially 3 key steps in any root finding algorithm. First, you want to guess 1 or more initial values for x. Then you want to iterate using a scheme to improve your guess. And then you want to check for convergence. So ask the question, has the improvement scheme of step 2 produced a result of desired accuracy? And if the answer is no, then you go back to step 2 and improve your guess again, and then check the convergence again until the answer in step 3 is yes, and then you can stop the iterations. The crux of the algorithm is often in the second step, and the objective of devising an algorithm is to get from the initial guess to the final result as quickly as possible, or in as few iterations as possible. So let's talk about the bracketing methods. So as you may have observed from the graphical methods, in most cases, the function changes sign around the roots of the equation. So here f of a is negative and f of b is positive, and we see that there is one root in between those. So in general, for bracketing methods, two initial guesses are used, which bracket a root. So one initial guess is on one side of the root, put a bracket here, and the other initial guess is on the other side of the root, and the root falls somewhere within that interval. And then with each iteration, the bracketing interval is reduced while continuing to bracket the root until the interval is small enough to achieve the desired accuracy. So we can introduce the intermediate value theorem here to kind of understand and help us with developing these bracketing methods. So the statement of the intermediate value theorem says that if we have a function on an interval from a to b, and it's continuous, and the function f at a, so f of a is less than or equal to f of b, then for every value of y in this interval, f of a to f of b, there exists some value of x on the interval from a to b such that y is equal to f of x. And the same applies if f of b is less than or equal to f of a. So basically, this is saying that if f is continuous, then for the values of f to change from f of a to f of b, it has to pass by every possible value between f of a and f of b. So we have some function here, and this is f of a, and this is f of b. Then for any value of y in this interval, I can find a value of x where y is equal to f of x. Basically, it's saying that my function has to attain every value of y between f of a and f of b. And so the consequence of this theorem is that if a function f is such that f of a is less than 0 and f of b, or less than or equal to 0 and f of b is greater than or equal to 0, then there exists some value x in this interval from a to b such that f of x is equal to 0. So that means if f of a is less than or equal to 0 and f of b is greater than or equal to 0, then there is a root in that interval from a to b. And then we can proceed to find this root x iteratively using either the bisection method or the false position method. As we saw graphically, when we define the bracket, several situations may occur. If f of a and f of b are different signs, then the interval from a to b contains an odd number of roots. If f of a and f of b are the same sign, then the interval from a to b contains either 0 roots or an even number of roots. And if f of a and or f of b are equal to 0, then a and or b are roots, which rarely happens that you would guess one of your initial guesses is exactly the root, but it can happen. Okay, so let's talk about the bisection method. So given a bracketed root, we want to repeatedly half the interval while continuing to bracket the root. So if we begin with an interval from a to b, and if f of a times f of b is less than 0, so essentially what this means is that the function changes sign from a to b, then an estimate for the root can be found as the average of a and b. So xi is the estimate of our root, is equal to a plus b over 2, or we could write it as a plus b minus a over 2. And then we want to test the function at this midpoint, so at x of xi, we want to find f of xi, and we want to then, figure out, basically do this test again with our midpoint to figure out which half the root is in, and discard the half that does not contain the root, and make our new interval the half that still brackets the root. So we can kind of see this with an illustration here. So we have this function f of x on some interval. We're going to choose our initial interval a to b, and so we evaluate our function f of a and f of b. And then we want to test if f of a times f of b is less than 0, we know that there's a root in between, so we find the midpoint as our estimate for the root, so xi, and evaluate the function at xi, so f of xi, and then we again use our same test to figure out which half contains the root, and discard the half that does not contain the root. So here f of xi times f of b would be greater than 0. So we discard that side. F of xi times f of a would be less than 0. So we know the root is on that side. And then we update our interval. So now our new interval, our new a and our new b are shown here. Again, we find the midpoint as our new estimate for xi, evaluate the function f of xi, figure out which side contains the root, and discard the other side. So we're going to discard this side here and make our new interval a to b shown here. Then we find the midpoint, figure out which side the root is in, and discard the other side, and make our new interval, and again find the midpoint. And we do this until the length of the interval is such that we achieve a desired level of accuracy. So to reiterate the procedure, the step 1 is to evaluate f of a and f of b to ensure that f(a) times f(b) is less than 0. Otherwise, if that's not satisfied, then we exit with an error and say either there's no roots or there's an even number of roots. So try again for your initial guesses. The next step is to calculate the value of the root in iteration I, as xi is equal to ai plus bi over 2. And then check which of the following applies. If f of xi is equal to 0, then the root has been found and we can exit. If f of xi times f of ai is less than 0, then for the next iteration, which we would say xi plus 1, is bracketed between ai and xi. And so we update our interval. So ai plus 1 is still just equal to ai, and bi plus 1 is now equal to xi. Alternatively, if f of xi times bi is less than 1, so this means if we have our interval here, this is our ai, and this is our bi, and this is our xi, this case number 2 would mean that the root is in this side, and case number 3 means that the root is in this side. So if xi times f of xi times f of bi is less than 0, then for the next iteration, xi plus 1 is bracketed between xi and bi. So we're going to use ai plus 1 is equal to xi here, and bi plus 1 is still just equal to bi. So then this would become our new interval. And then step 3 is to update our counter, so set I is equal to I plus 1. And then check if I reaches the maximum number of iterations, or if the convergence criterion is reached, basically that or whatever our estimate of our error is less than some specified error value, for example, then we would stop the iterations. And it's a good idea to specify a maximum number of iterations so that you don't get caught in an infinite loop or have your algorithm run for way too long. If there's something wrong or something off about the function or about the algorithm, then having a maximum number of iterations allows it to stop in a reasonable amount of time, and you can kind of check what's going on. So if either we didn't reach the maximum iterations or we have not reached the convergence criteria, then we go back to step 2 with our new interval and continue on. So I just want to make a note about the test for root bracketing. So we can use f of a times f of b is less than 0, as I mentioned. So this tells us if the sign is different between a and b. But this may actually fail in your computations if the function values are extremely small or extremely large, because this could cause either underflows or overflows in the computer. Another option in MATLAB is to use this function sine. So we could check if sine of f of a is equal or not equal to sine of f of b. And so this function is independent of the magnitude of f. So if you have some value f, the sine of f returns -1 when f is less than 0, it returns 0 when f is equal to 0, and it returns 1 when f is greater than 0. So this is just a built-in function in MATLAB that you can take advantage of to avoid this kind of rare case where this may cause issues. So we talked about the convergence criteria, so we need to define what our error estimate is and what we would typically use to decide when our method has converged. So the approximate relative error for the bisection method is epsilon r is equal to xi plus 1 minus xi divided by xi plus 1. So basically it's the size of the interval divided by, or it's our current estimate minus our previous estimate divided by our current estimate. So it's essentially this gives us an idea of the size of the interval divided by our current estimate. So when the absolute value of E or epsilon r becomes less than a specified threshold epsilon s, then the iterations are stopped. So we can do a quick example. So we have this function f of x is equal to sine 5x plus cosine 2x, and we want to determine the roots of this equation using these three different intervals. So we want, and our error threshold epsilon s is equal to 0.0005, and we want to determine the resulting relative error epsilon r for our final approximation. So first we want to find the root that's between negative 0.6 and negative 0.5, and then the root between negative 0.3 and negative 0.2, and the root between 0.6 and 0.7. So first thing we do is plot the function to see its behavior and kind of get an idea of where we're at. And so the first set, the initial guess is between negative 0.6 and negative 0.5, so we're looking for this root. The second one, we're going to be looking for this root, and the third one, we're going to be looking for this root. So I wrote a function in MATLAB to solve this, which I will post on eClass, and I'll just show the result here. So for the first root, we start with our initial guess of minus 0.6 and minus 0.5 for our A and our B. This shows the iteration numbers as we go down here. So then our first estimate of our root is the midpoint of that, so minus 0.55. Evaluate our functions fa and fb and f at xi, and then the approximate relative error. And so this is just kind of a sort of dummy value because we don't have a previous current and a previous estimate for this case, but all of the other ones are calculated. And so we see that we wanted to know when the absolute value of our approximate relative error was less than 0.005. So that happened here after 8 iterations, and we got our estimate of our root as minus 0.52363. The same thing for the second root. So here we're starting with an interval of minus 0.3 to minus 0.2, and we find after 9 iterations that the root is negative 0.22432. And for the third root, we're starting with 0.6 and 0.7, and we find that after 8 iterations, the root is 0.67324. And you can compare with this a function, built-in function in MATLAB called f0, which finds the roots of a nonlinear equation, like the one in this example. So we had sine of 5x plus cosine 2x. So you can use f0 which only actually requires a single initial guess. So if you use one of these bounds of the interval, you should be able to come up with an estimate for the roots. And that the MATLAB script plots our estimate at each of our iterations for each of the roots, shown as the circles here. So we start with an estimate a little bit away, and then we can see kind of as it goes, we can start to hone in on the roots for those 3 different roots. So for the bisection method, it is also possible to determine the number of iterations required to attain a particular error a priori or in advance. So if Vt is the true value of the root and Va is the estimate of the root, then we know that the absolute value of the error is the absolute value of Vt minus Va. And if our interval is from A to B, we can let L be the length of the interval, so B minus A. So the first estimate, x1, is going to be the average of this, which is a plus b over 2, which means that the next iteration, the length of the interval is L over 2. And if we continue on, the interval for iteration n has a length of L over 2 to the power of n. And we know that the true value exists somewhere in this interval of length L over 2 to the power of n. So that means that the absolute value of the error has to be less than that. So the absolute value of E is less than or equal to L over 2 to the power of n. So if we have a maximum desired error, if we want to know that for sure our error is going to be less than or equal to E max, then we can find out how many iterations we need to achieve that. So L over 2 to the power of n is equal to E max, which means that n is equal to the natural logarithm of L over E max divided by the natural logarithm of 2. So we can see another example here. So here we've got a polynomial function, f of x is x cubed plus x squared minus 10. And we want to determine first the number of iterations required to find a root of the function on this interval from 1 to 2 with the absolute value of the error less than or equal to 0.004. So without knowing the true value, without knowing what the root is, if I say that I want to guarantee that the true value of the error is less than or equal to 0.004, how many iterations is that going to take? So we can calculate that. And then we want to use the bisection method to find this root and calculate the relative error, epsilon r, as well as the true error. So to calculate the true error, we need to know what the actual root is. So the actual root with 10 significant digits is given by this VT here. So for the first part, we want to estimate how many iterations we need. So for the desired estimate of the absolute error, the number of iterations required, we said was given by this expression. So here we've got L is the length of our initial interval is 2 minus 1, which is 1. Our E max is 0.004. So that means our N is, we can plug these into our expression for N and get that it's 7.97. So we need approximately 8 iterations to achieve this error. So we can run this through the MATLAB code, which again I will post on eClass. And again, we see our initial interval from 1 to 2, our initial estimate of xi, and the upper bound for E is just the length of the interval. So it's L for each of these iterations. And so after 8 iterations, the upper bound for E is less than 0.004, which is what we predicted. The actual error is less than that, and the actual error was actually less than that in the previous iteration. But in this previous iteration, the upper bound was 0.0078. So we could not guarantee, without knowing the true value, we couldn't guarantee that the error was less than 0.004. So we did one more iteration. And then this continued on until 10 iterations and found the root at 1.8677. And this plot here again shows the value of the estimate at each of the iterations. So we start out here and then quickly kind of hone in on the value of the root. Now for a polynomial function in MATLAB, there's a function called roots, which allows you to write in the coefficients of a polynomial, and it will give you the values of all of the roots. So you can compare with our result here. And again, I will post the code for both of these examples on eClass. Thank you.